Our final lecture. Last time we began investigating the Stokes system, Stokes flow in the two-dimensional domain, if I'm not wrong, whose lower boundary is porous. The idea is to start from Stokes equations endowed with the Dirichlet inflow condition on the upper boundary, periodic boundary conditions on the lateral boundary, and we assume that a lower boundary has periodically distributed holes, and on each hole we prescribe the value of the normal stress corresponding to exterior conditions. And the idea is to use the method of asymptotic expansion and boundary layer analysis and try to deduce effective system consisting of the effective equations and, more importantly, effective boundary condition on the porous part of the boundary. I just need to see where we stopped and how did I label the. So this was the result from the appendix. That was the last thing. Okay. This was 4. Okay. So did we start from three-dimensional domain or
I think it's
two-dimensional? Yeah. And I put 0. Let me see. Q0. Then here it's not 0. It's Q0, I think. So in the system 4, right-hand side, first equation, what do we have? System 4. System 4. Where is system 4?
This is 5.
5.
I don't think I marked it. Oh, this is 4.
Yeah, this is 4. It's, what is this? Q0. So it's, here it's Q0, okay? Here, Q0. Okay. So, okay. You do not have to write this. So the idea is to approximate the unknown solution, which cannot, of course, be found analytically, with approximation denoted by a capital U, expanded in, you do not have to write this, you have this already. And the pressure of course, all these functions that we are going to construct are assumed to be periodic with respect to the first variable. So far, we have constructed, you have also this. You do not have to write. So we have this one. Y is the fast variable. have this one. It was the superscript. Okay, so for the zero order approximation, U0 Q minus 1, we propose this kind of ansatz, where this functions that depend on the fast variable satisfy system 5. Was it 5? Yeah. And then what we proved, due to the theoretical result that deals with Stokes system, possibly non-homogeneous, with the prescribed stress on the part of the boundary, is that this function W exponentially stabilizes towards a constant, while this that corresponds to pressure exponentially vanishes. And the problem for WKPK was formulated in a way that essentially we impose an additional condition such that this function here stabilizes towards a unit vector. And we can do that and omit the overposing of the problem by introducing the constants tau k, I think that it was tau k in the boundary condition corresponding to prescribing the stress. And by doing that, we essentially achieve that our zero order approximation outside of the boundary layer equals to this, while zero order approximation for the pressure equals to 0 outside of boundary layer. And now what do we have to do? We have to look at the problem for first order corrector, and then in a similar fashion seek for the solution, and then using system 4 that we obtained from the boundary condition on the porous part of the boundary, deduce the effective boundary condition. In order to deduce the effective equations, which will remain unchanged, and that is a less interesting part of the result, we need to go further and compute the second order corrector. Okay. So if you recall, we also had that. The problem for first order corrector was, after plugging this expansion into the boundary, into the Stokes system, was essentially the following one. So this was the equations from where we will deduce the problem for U1 Q0. If you observe this more closely, then you will see that in the equation for U1 Q0 we have terms that we already constructed here. And now, if you look more closely, I will not write them. So we have a derivation with respect to x. That means that here we have separation of variables. That means that here we will have some partial derivatives of these functions. Excuse me, not this one. This is the unknown. This one. Okay? So again, we have this guy here. Again, with respect to this. And here again, with respect to this. Okay? So let me write it. So if we compute this from there, and we have this. We compute this guy here, and we have something like this. I'm not writing the dependence on the variable. We know that uk depend on x, while wk and pk depend on fast variable. And now if we integrate this with respect to the first variable and use some technical results that are also proved and using the fact that then we from here immediately deduce that equals to 0. Okay? So we deduce that our effective velocity, and this is our effective velocity, satisfies the zero divergence condition. Okay. And now we still need to compute this guy here. This guy here can be computed as following. And now if you look in all these terms, partial derivatives of the u1, u2, partial derivatives with respect to x, of course, of u1, u2, partial derivatives of u1, u2 with respect to x. And that all suggests us to seek for the u1 and Q0 in what form? Okay, we will use another. So we need to incorporate this term, and then we will deduce, we need to introduce a second set of auxiliary problems in order these equations to be satisfied. So definitely we will have these partial derivatives. Again, we seek the solution such as in a way that the variables are separated. And now we have to introduce another set of auxiliary functions, which depend on two indices. We will denote them like this. Okay? So the expressions for the terms that are essentially known, because in the last step we constructed the zero order approximation, suggest us to seek for the unknown first order corrector in this way. So these guys here need to be incorporated definitely, because all these known terms contains them. And then we introduce the second set of auxiliary functions. Before writing down the problem for second set auxiliary functions, W and P, we have to observe one more thing. Our effective velocity was U, U1, U2, okay? But our effective pressure outside the boundary layer was equal to 0, and we have to have pressure in the effective system. So here we add a function which we denote by theta 0 that depends only on this variable, and this will be our effective pressure. So this is effective velocity, we have this already written, and this will be our effective pressure that will appear both in the effective equations and effective boundary condition. And now, first, we are going to deduce the problem for this. How we do that? We do that in a way that these equations are satisfied. Okay, now I will erase this. Okay, so the second set of auxiliary problems reads: okay, so why is this the first equation satisfied by WP? Because, see this guy. This guy is from this guy, okay? So we have to take care this. This is, of course, from this. This is, of course, from this. And this is from this guy here. But throughout the process, we have to have in mind that when we pose auxiliary problems, that we must assure that they are well posed. And the well posedness is given by our result from the appendix. It was a theorem that I wrote. So we have to have in mind that the right-hand sides, both in the equation and in the boundary condition, have zero mean value. In this case, this is satisfied. However, when we consider this, from this guy here, we obtain this. From this guy here, we have, excuse me, this is a scalar function. And then we cannot simply put equal to 0, because due to result from the appendix, we have to have that right-hand side, and in this case, this is right-hand side, has 0 mean value. And we know that these integrals are not 0, but that it holds something like this. With respect to the first variable. So we do not put here simply 0, because then we will not have the well-posedness of this problem, existence, uniqueness, and of course exponential decay. But we put this in order to assure that the mean value with respect to the first variable equals to 0. And now, taking into account the boundary condition on the holes, we deduce the following. This is the term, this is matrix. Stress tensor is a matrix, and then this is the element in the first row and second column. And now again, if you look more closely on this theoretical result regarding the general boundary layer problem, we have to assure that this also equals to 0 when we take mean value with respect to the y1. And that's why on the right-hand side we put this. So remember, this superscript n corresponds to holes. Superscript d corresponds to the solid part of the porous boundary. The second component reads as follows. And again, we have to assure that the right-hand side of the boundary condition has 0 mean value. Okay? And then you write it below. I will write here. We have on the solid part Dirichlet boundary condition. And of course we have to keep on the lateral, we have to have the periodicity with respect to the first variable. So let this be, did we label this or not? No, okay, then we will label just this as 6. Okay, so you write it below, I will write it here. Very important, as I mentioned several times, the right-hand sides in 6 are chosen to keep, let us say, to keep integrals with respect to first variable equal to 0. And by doing that, we assure, due to the result from theorem, that we have the well-posedness and exponential decay towards 0. So there exists some constant vectors such that exponentially. Okay? If you recall, in the problem for WKPK, we additionally required that the velocity part exponentially stabilizes towards a unit vector. We did that by imposing constants tau k in the problem, in the boundary conditions resulting on the holes. Here we do not do that, and for that reason, we do not know whether these constants are equal to 0 or not, at least some of them. But this is not needed, because at this point we can deduce the effective boundary condition. And these guys here will appear in the problem for this, and from the problem from this, we only deduce the effective equations. Okay, so now we go back to 4, where we have Q0, P0. Isn't that 4? Yeah. Okay. Now, going back to 4, I don't know what to erase. I will erase this. Going back to 4 and taking all this analysis into account, we deduce the following. That Q0 is equal to this, plus something that is of order epsilon and lower, and this So this is the system satisfied by our effective velocity and our effective pressure on the porous boundary. And now, we want to write it in a way that something can be deduced from it, to say what type of boundary condition we essentially derive. In order to accomplish that, we introduce the effective stress tensor. What that means? That means that we compute the stress tensor satisfied by our effective velocity and pressure. It is, according to definition, this plus this. So this is effective stress tensor. Then we compute the effective stress and decompose it in this part and this part. If you recall, at the very beginning of the analysis, we computed this. Now we just have to apply the effective velocity on this operator. So this is effective stress. And we can see that it is decomposed with respect to the first unit vector and second unit vector. So we can denote this guy as its normal part, and this guy here as the tangential part of the effective stress. So this component is tangential part, denoted by ST, and this component here is the normal part, denoted by SN. And now from the system that I denoted by 7, so please denote this 7. We can deduce by introducing the effective stress and its corresponding components, we can deduce this. These constants, if you recall, are from the problem 4, yeah? Not 5. Problem for WK, PK. And they are given from this problem, because that problem essentially contains 3 unknowns. Triple is the solution. WK, PK, and this constant tau k. So we have this from the first equation, and this from the second equation. These are the components of the exterior conditions, while this K epsilon is given like this, and it can be interpreted as the normal permeability of the boundary. Okay? So, this was formally written. I just introduced these components of the effective stress in order to get something that has a name, you know? So if you look more closely to this equation here, then it is obvious that it can be viewed as a version of the Beavers-Joseph law. And Beavers-Joseph law claims that the shear stress on the boundary is proportional to the slip velocity. The shear stress of the boundary is proportional to the slip velocity, okay? And of course, since we imposed the exterior condition, we have, in this case, the contribution of the exterior condition. On the other hand, the second equation in this system that I will label as 8 is essentially a Darcy-type law saying that the normal component of the velocity is proportional to the difference between the exterior and interior pressure. In our case, not exterior pressure it is, but we have here the normal stress, okay? So this analysis of ours yield new type of boundary condition, which is essentially of the Darcy-Beavers-Joseph type. So again, the first component is, the first equation is a version of the Beavers-Joseph law, which states that the shear stress is proportional to the slip velocity in the absence of exterior conditions. Since we impose the first component, then we have its contribution. And the second equation essentially can be viewed as a Darcy boundary condition. As a Darcy boundary condition, saying that the normal component of the velocity is proportional to the difference between interior and the exterior pressure. In our case, not the interior pressure, but the normal stress. And this is the main contribution of our analysis. It's interesting to mention that in 3D case, so this can be remark 2. Let this be remark 1. In 3D case, the equations cannot be separated. Separated. That means that if we do not impose additional assumptions on the geometry of our porous boundary, then we just obtain a Darcy type boundary conditions which cannot be separated in the part satisfying the Beavers-Joseph and the part satisfying the Darcy condition. But if we impose some additional assumption on the porous boundary, then it can be done even in the 3D case. Okay, all this can be rigorously justified. The idea of rigorous justification, I almost forget one important thing. I will not go into details, I will just erase this. And say that by constructing U0 Q1, and we construct them by using the construction for lower order terms, we deduce, and of course introducing another set of auxiliary problems that will contain 3 indexes, we deduce the effective equations satisfied by effective velocity and pressure U theta 0. And as I indicated before, we already, if you recall, obtained the zero divergence condition. For the momentum equation, we obtain Stokes system, which was to be expected. our main aim here was to derive the effective boundary condition. Okay. On the upper part where we have the inflow condition, I will erase this. You have this. This was the given function. Of course, we have to keep all functions periodic with respect to the first variable. And then we put this condition, but we write it in the following form. If we introduce matrix K epsilon as this one, so this is matrix, and this is here a scalar, okay? So if we introduce this matrix here, note that this guy is essentially this guy here, yeah? So if we introduce matrix in this way, effective boundary condition can be written in the following form. This is effective stress. And this H, if I recall correctly, was Q0 P0. So we just wrote these two equations compactly. Okay? On the porous part of our boundary. And if you look just this, then this is Darcy type boundary condition. But in 2D case, it can be separated and written like this when we obtain the Beavers-Joseph and for the normal component Darcy. In 3D case, we obtain something like this, and it cannot be straightforwardly separated without taking some additional assumption on the geometry of the pore. One more thing, and that will be essentially final remark. Remark 3 is that if you look more closely on this system, does it still depend on the epsilon? The functions effective velocity and pressure do not contain index epsilon, but this system, satisfied by the effective velocity, essentially depends on the epsilon, because this permeability matrix, this normal permeability, this Beavers-Joseph contains epsilon. Now the natural question would be, can we put epsilon equal to 0? If we put epsilon equal to 0, what will happen? That will mean that the effective boundary condition on a porous boundary is essentially the Dirichlet boundary condition, isn't it? And then this problem is not well posed, because we have this inflow condition and the compatibility condition will not be satisfied. So remark 3 would be that effective problem nine depends on small parameter epsilon, and we cannot simply put epsilon equal to 0. The explanation is that compatibility condition would fail because integral of this is not equal to 0. And that means that again we have here a singular perturbation problem with respect to the small parameter, and that means that we can now construct the approximation for the effective velocity and pressure. And that is also done in this paper, and that is done for the purpose of rigorous justification. Okay? But I think that the main results are this one, and if you want to see the details of rigorous justification, then you can look in the paper published by Edward and myself in SAMP. And if you want to look what happened in three-dimensional case, where we cannot simply separate Darcy type boundary condition as Beaver-Joseph law and Darcy law, then you should look at our joint paper published in International Journal of Engineering Science. And this concludes this lecture, and this was the final lecture of this PhD course. I thank you all for attention, and that will be all if you have no questions.